Hello, I'm Behrad Gholipour from the Nanoscale Optics Lab here at the Electrical and Computer Engineering Department at the University of Alberta in Edmonton, Canada. And I'll be giving you a talk on energy efficient, classical, neuromorphic quantum computing and telecommunication platforms and activities that we're generally pursuing here at the Nanoscale Optics Lab at the U of A. So it's a pleasure to be able to talk to all of you, and show you some of the things that we're doing in regards to trying to create the next generation of really green computing platforms. So just to give you an overview, what we're looking at is trying to create platforms where you have sustainable green computing and telecom. What does that mean? That means that we're trying to develop technologies where we're using less energy in our devices. We're trying to create platforms where we can create both sort of non-volatile transitions, and I'm going to talk a lot about that in the coming slides, which is a major paradigm shift in the world of computing. And this allows us to be able to drastically cut down on the energy that we consume within our computing platforms. And we're also looking at metasurface enabled sort of photovoltaics and trying to find ways to increase the absorption efficiency of various photovoltaic systems and devices by just designing them in very specific ways to be able to enhance light matter interaction. So what we're really pursuing is two sets of technologies, one on the demand side and one on the supply side. On the demand side, we're really looking at trying to create a new generation of fundamental building blocks for various telecom and computing platforms that allows to be able to have a major reduction in power consumption, but also by sticking these to emerging protocols like neuromorphic computing and quantum computing. This allows us to be able to deal with much larger data sets and big data platforms and big data applications in a much more efficient way. So the protocol is important, the component level is important, and we're trying to tackle both. And as I said, on the supply side, we're looking at creating a whole new generation of sort of photovoltaic cells, regardless of the material system that the solar cell is made from, by coming up with some universal design sort of principles. We can increase the total absorption of our photovoltaics, or create building integrated photovoltaic devices which have various colors and are aesthetically pleasing and can be integrated within various sort of infrastructure and architecture within cities and so on. So with that in mind, the approach that we take is one which is based on the following sort of pyramid of activities. We generally identify a particular application that we can target in the short to medium term, based on the material systems that we have available to us, and also the sort of design space that is available. Once we've identified these applications, we very carefully engineer the material system. So to be able to make much more efficient computing devices and photovoltaic devices, you really need to make sure that you start off with the right material. You can't just take any material off the shelf and hope that you can get something that's going to be record breaking or create a major step change in the sort of efficiencies or the power consumptions of these platforms. So we very carefully engineer our materials. Once we've identified a particular material system, we very carefully engineer it by what we call stoichiometric engineering, which I'm going to cover in a couple of slides time. Excuse me. And once we've done that, we have the right material system, we've characterized it fully, and we understand exactly what the parameters are there. We use inverse design and forward design techniques to create various devices, various photonic devices, various nanostructures that would enhance a particular metric in the context of photovoltaics, absorption in the context of computing devices, usually power consumption and speed and modulation contrast. And we use inverse design. What inverse design means that we use various optimization and AI algorithms and ML algorithms to be able to design devices where you've got a lot of various parameters at play. So once you have a lot of parameters at play, it's nice to be able to use these inverse design techniques to try and sort of optimize multiple parameters to be able to get to a sort of application-driven metric that you're trying to enhance or optimize for your application. So inverse design techniques are a major it's a component of all optoelectronic device design, I would say, in the coming decades. So that's what we do based on the materials that we make. Once we've got the material system and the device component level completely designed and optimized, then we go on and integrate them with optical fibers or waveguides in the case of telecom and computing, or in the case of photovoltaics, we combine them. We take our design principles and we combine it with various widely used material systems like perovskites or silicon to try and enhance these existing solar platforms. So I'm gonna start off by giving you a little bit of an overview of what I mean by design and materials, what I mean by stoichiometric engineering of these materials. So for photovoltaics, for green computing, we really need the right materials, as I said. What I call design and materials is a manifestation of this particular technique that I'm going to cover for you here. So the design, whenever you have a particular material system, in our case, we take usually sort of binary or ternary or quaternary alloys of various materials that are useful to computing and photovoltaics. And instead of just making one particular composition, testing it out, hoping for a good response, then going and making another one and testing it out again, hoping for a good response, and slowly making your way through the parameter space. The alternative to that is what we call stoichiometric engineering or high throughput material discovery. This allows you to, in a very rapid way, screen and optimize your material system. And the way that's put together is as follows. You can take any sort of PVD chamber. This is a physical vapor deposition chamber that can be made up of electron beam sources, evaporation sources, plasma sources, so sputtering, evaporation, or various other PVD techniques. All of them you can use this with. And what we do is we put a little wedge between our sample and our sources. And by controlling the position of this wedge, what we can do is we can create very controlled thickness gradients of various elements that we're making as part of that alloy that we're trying to sort of deposit. So if you have a fictional material system, let's say ABC, by putting these wedges in front of the different sources, you can create different gradients of these materials, different thickness gradients of these materials on your sample substrate. And as soon as you co-deposit all of these together, you basically can create a situation where across a single substrate, you've got an alloy being deposited that every single different position has a slightly different composition. So you can come up with a sample once you've optimized the positions of your wedges that contains 30, 40, 100 different to 100 different alloys, really, depending on whether you put discrete masks on or you have a continuous film as we have here. And by just screening and characterizing this one sample, you can create a huge data set that allows you to be able to very carefully pick the composition that's best for your application. Your application works at this particular wavelength range and needs these particular losses and these particular absorption levels. Here you go. You can very quickly point to the place an alloy composition on your sample that allows you to be able to achieve your maximal sort of operational metric. And this is a very universal technique. You can do it with various different material systems. It doesn't really discriminate against the material system. It's just a PVD technique with some spatial considerations. And through this, you can very quickly optimize your samples, your material system. So I show you here an ellipsometry, variable angle spectroscopic ellipsometry measurement of one of these samples. Show you the real part and imaginary part of the dielectric function, the permittivity, if you will, which determines for us our refractive index. In the case of photovoltaics, this is very important, our absorption levels. And in the case of computing, allows us to be able to understand how we can integrate these with different waveguides and different optical fibers. And what you can see here is what I'm showing you here is the real imaginary part, and we're cycling through the wavelength here, as you can see. I've just picked a random alloy, and we've done many different alloys over the years. Antimony telluride here is one alloy that we're quite interested in. It has a lot of good switching capability, but also has some interesting functionality for photovoltaics, which we're looking at. And as you can see, we start from about 200 nanometers, and you can see some areas have very negative epsilon 1, some areas have very high epsilon 2, so we can identify areas where we have plasmonic properties, some areas where we have high index dielectric properties, and this allows us to be able to design our photovoltaics and a computing system components in a very, very careful way. Imagine that by just adjusting your composition, you can turn a material system from plasmonic to dielectric, and this has major implications in the operation of your devices. If I take this wavelength and I put it now on the x-axis, and I show you a couple of different material systems. Firstly, with a view, we'll firstly look at some of the green computing projects that we've been looking at, and you can see a couple of these different alloys, and you can see all of them have a similar sort of they have a similar sort of dispersion. This is a real part of permittivity. And in particular, the alloy systems that we look at are very interested in, because of our applications that I explained before, are the Chalcogenide family of materials. Chalcogenides are usually alloys of metallic alloys, usually of sulfur, selenium, and tellurium. They can have low refractive indices. They can have high indices, more than n equals 8. Which is very unprecedented. They can have plasmonic properties, as I showed you, or epsilon near 0 properties, which is, again, an area of very sort of intense activity these days in the area of nanophotonics, in the world of nanophotonics. So they have very similar dispersion. What you can see is they're high index dielectrics across much of the telecommunication band, which is important for your broadband and internet-based technology platforms. They are plasmonic across much of the UV invisible part of the spectrum, and they have these epsilon 1 equals 0 points, which is useful, as I said, for epsilon near 0 applications. So you can see here that I've just taken one of the alloys, again, antimony telluride, as our case study, and by changing the composition of tellurium between 92 to 11%, you can see that we can change the plasmonic band effectively of this material, and by definition also the losses, the absorption levels that the material enjoys across the visible near IR to sort of telecom band. This is a drastic change that we can induce by just changing the composition. So really, we're not at the mercy of whatever's on the shelf. By changing very carefully these the composition of these different alloys, you can create vastly different materials that are very targeted to the wavelength of operation that you're intending to use your device at. So just to give you an overview of what can be done, for example, on the ternary side of things, if we take not antimony telluride, we add a bit of bismuth in there, bismuth antimony telluride, and you can see that we can look at the dielectric properties, the plasmonic properties of the material system, where you got on the dielectric side of things, we define a figure of merit, n equals n over 4 pi k, at 1550 because of the telecom band applications of that wavelength, and you can see that in this particular case, what we would want is a high refractive index and a low loss in telecom applications, and much more high absorption in the visible part for photovoltaic applications. So you can see that you can clearly identify that closer to the binary side of the things, binary compositions, you've got a much better figure of merit here. So these binary compositions are very good for telecom band, and these ternary compositions are much better for photovoltaic applications. So computing is in the binary, and photovoltaic seems to be more akin to the ternary side of things. And if you look at the plasmonic part of plasmonic properties, you can see again that the plasmonic Compositions are generally the ternary compositions, much more heavy on the bismuth side of things. So the metallic, obviously, component increasing in that alloy gives you a much more plasmonic response, but a huge plasmonic window variation that we can tune across by just changing the composition of the alloy. And again, epsilon near zero applications are also important and widely useful these days. And we look at the losses there, the epsilon 2 at near IR and Z points. And that also gives us application for some so it gives us some information from some other applications that we've published on previously as well. Just to put things in context, look at what this can bring you, just as a measure of what is possible here. If we plot this material system that we just looked at, bismuth antimony telluride, BST, and we look at a plasmonic figure of merit and a dielectric figure of merit. Plasmonic figure of merit just indicating how many plasmonic wavelengths a plasmon can propagate before absorption, basically sort of reduces the energy to, and absorption really kills that plasmon as it's propagating. So dielectric figure of merit is a slightly different case, where again, as I said, n over 4 pi k, we're looking at holding a particular wave in a dielectric medium within the dielectric medium and not dissipating the energy as much as possible. So so you can see that if we compare these various widely used material systems around photonics and nanophotonics and optoelectronics, gold, silver, and aluminium have been for many years the stable of plasmonic materials. When people generally talk about plasmonics, you think silver and gold, but you can see that by tuning the composition, we can see that BST at UV part of the spectrum becomes a much better plasmonic material than the classic metals. That's an interesting fact that we did not know before, and this allows us to be able to have a composition tunable plasmonic material. These are single line because they cannot be tuned. BST is an alloy that can be tuned very carefully, so this gives us a much more flexible material platform to deal with these wavelengths. Aside from that, you can see that as we go further and further into the infrared part of the spectrum, the Chalcogenide material family really starts to get better and better as the transparent conductive oxides start to reduce and absorption kicks in for them. BST and these Chalcogenide material families that you can tune very carefully give you a much better response at these wavelengths. And again, they're not single element materials, so you can tune them very carefully. So some very interesting facts that you can see, and this allows you to then integrate these into your materials, into your devices, and have all the goodness of, for example, gold and silver in a material system that's switchable, that's tunable. In a material system, not like TCOs, that doesn't have to be, that can be tuned across various wavelengths, and it can exist in amorphous or crystalline. Can have high levels of nonlinearity, low levels of nonlinearity, high levels of absorption, good photovoltaic properties, and so on and so forth. You're opening up your sort of device design and your platforms to much more adaptive and flexible material platforms. So with that, let me talk a little bit about some of the platform devices that we make out of these material systems. And as you can see here, it's I'll just move this somewhere here. So telecommunication platforms currently are extremely efficient in some ways and extremely inefficient in other ways. So of course, telecom has really rapidly grown in the last decade or so. We have a huge number of new technologies entering the market every day, really, and it has really tried to keep up with the explosive growth of data demand that societies around the world are creating as a result of various new activities, new commercial activities, and economic activities that we're all engaging in across the globe. So in some ways, we've managed to be able to send signals around the world in very fast ways, but in many ways, we're very inefficient in doing so. If you look at a global map of the sort of a heat map of the entire planet, you can see that we have major hotspots on the planet now where data centers, the various data centers that we have powering the internet, the backbone of the internet, are creating huge thermal footprints. So as you can see here, I'm just showing you a thermal map of a standard data center with the racks. A huge amount of power is lost in these racks and in these data centers, as heat, as lost energy, as lost light, as you're multiplexing between a fiber and a chip, back and forth. We have these major bottlenecks in our systems where we send our signals long haul through optical fibers, through light, but then we do most of our processing and electronics, so we have to convert optical to electronic signals, and then once the processing is done, then convert them back and send them out again. So these are major bottlenecks, major losses, major thermal footprint issues that are created as a result of these systems that we have these hybrid systems where we keep having to create these sort of conversions. That, as I said, gives you data latency issues, high power consumption and heat generation. And aside from that, just from a reliability standpoint, every time we've got an engineer that takes the fiber up and puts it back in, as much as we spend billions of dollars trying to optimize these connectors, there are coupling issues, coupling efficiency issues, and run-to-run issues. So the coupling from fiber to fiber, every time, fiber to chip, every time is slightly different. It's not always the same every time you take the fiber up and put it back in. So we're looking at whether we can have a monolithic system that allows permanent alignment, seamless integration with optical fiber platforms and waveguides, and allows us to be able to save on these bottlenecks and also on these heat loss and energy loss issues. So I'm just going to bring all of this on. So some of the things that we've been looking at is putting entire devices not on a chip, but on the tip of an optical fiber, on the side of an optical fiber. So can we bring the entire chip platform onto the fiber itself? Can we have fully fiberized systems where the entire information processing and all of the sort of signal processing, information processing is done entirely on the fiber, and we don't necessarily need to keep converting to chip and back and create all those losses. So we're looking for integrated multiplexing technologies. I mean, in particular, we're looking for temporal and spatial control of optical signals. So we want to be able to control these signals in time and in space on these optical fibers, with a view to routing fiber to fiber and fiber to free space. And be able to have tunable connections, because we want to be able every time to adjust everything and have everything be programmable, right, and down the line. So what we've been looking at is putting these chalcogenide material families, which I showed you before, various chalcogenide material families, and we nanostructure these materials with very carefully based on sort of plasmonic or me-type principles that allow us to be able to have very specific resonances or very specific dispersions, very specific absorption losses, insertion losses at particular wavelengths of interest. We put these, and we call these nanostructures metamaterials, metasurfaces. Metasurfaces are just sub-wavelength nanostructures that give you an overall effective response that you can then tune to the wavelength that you desire. So we put these on the tip of optical fibers. We put them on the side of polished optical fibers. In this case, we can polish the side of an optical fiber very close to its core, so we can deal with the leakage or actually control leakage from the core of an optical fiber into a particular flat planar chip-like surface. So you can see how we're bringing the flat planar chip environment to the side of an optical fiber, where everything is constantly being multiplexed and constantly being interrogated. The other thing that we're looking at in terms of applications, and this also feeds into the photovoltaic work, is looking at using various AI and ML algorithms to create metasurfaces that allow us to be able to control the direction of light upon transmission or reflection on a particular structure. And when I say direction, I mean we can change the direction of an incoming beam. We can induce what's called asymmetric transmission, which allows us to be able to capture a wave and not let it go back out again. Obvious applications of photovoltaics, and other things like trying to replace the liquid crystal on silicon in wavelength selective switches and telecommunication networks. So telecommunication networks right now, a major backbone of most telecom networks is what's called a wavelength selective switch, a WSS. And these WSSs are effectively just routers. They're a bunch of optical fibers that through through various optics and a liquid crystal on silicon programmable surface processor, photonic processor, can route the signal from one fiber to the next. So the light comes in, we have some photonic processing, and it's reflected into another fiber based on demand and based on the sort of signal that is being processed. This is a big device, right? You can see how routing between different optical fibers across a telecom network is effectively the backbone of what we're trying to do in most telecom situations. They rely on liquid crystals and they rely on MEMS. So they're very volatile systems. They have lots of drift and noise. Lots of power needs to be pumped to them continuously because liquid crystal and MEMS needs you to pump electrical or optical supply to the system continuously in order for you to be able to keep the system at a particular level, particular state. We're trying to transition these systems from these volatile paradigms to non-volatile paradigms, where you only put power into the system to be able to switch it from one state to the next. You don't need to keep powering it to be able to maintain that state. So this non-volatile switching that we're trying to bring in through using Chalcogenides metasurfaces allows us to be able to do non-volatile switching, low power consumption, and as a result, much lower thermal drift and crosstalk. And as you can understand, if you're not powering the device constantly and you're just trying to power it every time you're switching something, you've removed most of your power budget. You don't need to be pumping as much power, so the consumption goes down drastically as well. Another thing that we are looking at quite extensively is trying to create these sort of waveguide integrated devices. So at the moment, we're going from a pure electronics realm to a much more optical and optoelectronic sort of computing and telecom platforms in the coming decades. You can see, you may be aware already of the explosion of silicon photonic devices around the world these days. There is lots and lots of research being done by both industry and academia on silicon photonics and waveguides for data centers, very compact chips, for data centers, computing, and other things, including LiDAR. So in a commercial environment, in a manufacturing environment, a complete photonic system is not going to be built in a single factory. What's going to happen is you're going to have various different factories, various different foundries around the world specializing in different chips, different components. And as a broad system, when you're trying to make these complex systems, you're going to have to deal with multi-chip platforms, where one part of your system is being made somewhere, the other part is being made somewhere else, and you're going to have to connect these all up together. So the idea of having what's called interposers, that allow us to be able to connect between different chips, and things like photonic wire bonds that allow us to be able to go from one chip to the next in a larger system is very important. And we're very interested in trying to create tunable connectors, tunable fabric in these environments. So we want to be able to put these fibers from one chip to the next, and at every connection be able to adjust this. So if you have variations in your system, or if you're trying to adapt and change your system based on the incoming data in all these smart systems that we're trying to develop in the coming decades, you need to have variability, you need to have programmability, you need to be able to tune every connection, multiplex every signal in a very adaptive and analog way as much as possible. So you don't want static fabric, you don't want static connections, you want to be able able to have more these environments where you can have flexible connectivity, low latency, but also be able to have sort of fabric that allows you physical disk aggregation, but also post-connection, a degree of adaptability, a degree of tunability. For that, we're looking at things like grating couplers. We have reconfigurable grating couplers that we've made, and we're looking at for these platforms, for silicon photonic platforms, and we're also looking at drastically reducing the footprint of modulators in data centers and waveguides, silicon photonic architectures, by combining them with phase change materials and chalcogenide semiconductors as a way to have this non-volatile switchability. So I've talked a lot about these chalcogenides, and I just want to sort of drive home the point here. The chalcogenides, as I said, are alloys of sulfur, selenium, and tellurium. They have very interesting properties, as people are not aware in the audience. They have some of the highest nonlinearities, optical nonlinearities. This is nonlinear refractive index that we're plotting here of any glass. So if you look at the silicas and the calcium fluorides here, which are very widely used in optoelectronics, the nonlinearity of these glasses, the chalcogenide glasses, the metal-Chalcogenide semiconductor, much, much higher. So if you're looking at nonlinear properties for sensing or for telecom or various other applications, they are much, much more attractive as a material system than the classical glasses and the oxide glasses. They also have very wide transmission windows, so SiO2 ends around just below 5. The sulfides, selenides, and tellurides can stretch the transmission window well into the mid-infrared part of spectrum, covering the entirety of telecom band. As I said, the sulfides, for example, many of them are transmissive across the visible all the way to the mid-infrared. That is an unprecedented transmission window that you can use for all sorts of different applications. And most importantly, as I said, they can be optically or electrically switched between two different states, amorphous and a crystalline state, and this is a non-volatile transition. So you don't need to keep powering it once you've made the transition. You switch the device, from one state to the next, it stays there until you come and switch it back. So this is a fast, low power, non-volatile switching mechanism, and it also has an optomechanical component to it as well, if you wish to exploit that. Again, another thing that I just want to highlight is these metal-Chalcogenides are really a wonder material system. They're one of the few systems where they can exist in almost an unprecedented number of different chemical and geometrical forms. They can exist in nanowires, nanoparticles, monolayers, fibers, topological insulators, 2D materials, or superconductors. So really, they are a playground for industry and academia to look at emerging applications. So, as I keep banging on about the switchability, much of what we look at is not just making a device for today, but making a device that then, once it's field deployed, is adaptive, is switchable, is programmable, is some form of tunability is involved. We want to be able to switch these devices based on environment, based on application, based on stimulus, and have an adaptive system. So the phase change functionality that is at the heart of what I keep mentioning here is as follows on an atomic level. These materials, they can switch between a crystalline and an amorphous lattice. This can be induced optically or electronically, or even through thermal means. In the crystalline lattice, we have a very ordered lattice, so there's long range order in this lattice. In the amorphous phase, you generally have short range to medium range order, and this manifests itself as a drastic change in reflectivity and resistivity. The amorphous phase has a low reflectivity, is very transmissive, but it has a high resistivity because of all those electron scattering at the boundaries that you would anticipate. In the crystalline case, we have high reflectivity. It's a much more crystalline material, and it has a low resistivity because of the nice lattice ordering. And switching between these, it can be induced by singular pulses or trains of pulses, depending on the protocol you're using. In one case, from crystalline to amorphous, you melt and quench the material very rapidly, on the order of nanoseconds to picoseconds, and in some cases, people have demonstrated femtosecond melt quenching. And also, the annealing process itself is just another pulse with a slightly longer period. You don't need to make it as sharp because you're not trying to quench the material through your pulsing protocol. And just annealing the amorphous to crystalline, again, in the order of nanoseconds, you can switch the material back to its crystalline phase. And once you've switched it, you don't need any more electrical or optical supply. It stays in that state until you come back and change it. So you don't need to maintain the device in that state with energy. A major reduction in energy consumption. Across much of the telecom and the visible band, this induces huge amounts of optical change. So you can see here between amorphous being in blue, crystalline being in yellow, we have a large change in the visible and a much larger change in the infrared telecom band of the spectrum. And you can see, for example, very peculiar, this is the only material system that can switch between a plasmonic and a dielectric response across the visible band. This basically means that this material system, in this particular case, the alloy I'm showing you is germanium antimony telluride, GST, very common material used in industry. And you can see that this is a material that changes between being a metal and a glass invisible part of the spectrum. That's a very, very interesting property that no other material system exhibits, switching between a metal and a glass in a non-volatile way, and in the telecom band, it switches between a high index dielectric to a much higher index dielectric, if you will, as well. These materials can be deposited using very typical PVD techniques, CVD techniques, as I alluded to in the stoichiometric engineering section, and they have these very nice plasmonic dielectric transitions, broadband changes in optical properties, and very fast switching, as I said, and reversible switching has been demonstrated by many different people. So just to give you an outlook, across the telecom band, you have as large as a 2.5 change in refractive index. If you're familiar with much of the switchable materials that we use in optoelectronic industries and computing industries, the refractive index that we generally look at in these systems in lithium niobate, for example, or in the silicon derivatives that rely on thermal optic properties, or even ITO with the carrier modulation and the transparent conductive oxides, there are refractive index changes on the order of, maximum 0.4, 0.5, really much lower than that in most cases. This is a much larger change in refractive index, more than 2.5 in N. This is huge. A modulation contrast can be very large, signal to noise ratio can be very large, and as I said as well, this is a non-volatile transition. So just showing you a couple of different alloys that are available and being widely used across many different industries and companies and academic groups these days. GSST, antimony selenide, SPS, these are some of the major alloys on the menu. Each of them have slightly different optical properties. So depending on your application, your wavelength of operation, you're going to choose the one that best suits you in terms of losses, in terms of the refractive index and the contrast that you need. And we make these, as I'm going to mention again, we make these routinely, all of these materials in our lab here at the University of Alberta. So just a couple more sort of specific words on metamaterials and metasurfaces. As I said, we take all these materials and we make use of these transitions that they have, and we tailor their optical properties and these transitions to a particular wavelength of interest. We don't just, so we first design the material in terms of the atomic structure, we create the right composition that we need. Then what we want to do now is take this material system that's switchable, that has the right composition, and we want to now nanostructure it in a very careful way to create the right light-matter interaction with a view to the photovoltaic or the computing devices that we're trying to make. So we use what's called a metamaterial metasurface paradigm concept. And metamaterials and metasurfaces are effectively the paradigm is a very simple one. Metamaterials and metasurface allows to engineer novel and exotic macroscopic optical properties by structuring and combining materials, metals or dielectrics or combination of them at sub-wavelength scale. So we structure things on a very sub-wavelength scale that the wavelength of light cannot see these nanostructures. It only sees the effective average medium properties. But we've very carefully engineered each metamolecule, each of these little nanostructures, nanoresonators, so collectively they all couple together and have a response that the wavelength of operation sees as something that's effectively sort of has a particular property, particular index, particular loss, particular transition in refractive index at those particular dispersion at the wavelength of operation. So this particular paradigm has given rise to a large number of different demonstrations over the last 2 decades, a decade and a half, really. People have shown things that are not available in nature readily by just nanostructuring things in a very particular way. People have shown negative refraction, zero index materials. There's a large part of the community looking at cloaking technologies, giant nonlinearities. So by adjusting and tuning the light matter interaction in a particular material system or device, you can very carefully enhance properties like nonlinearities, create ultra thin super lenses, or make hologram devices for emerging display platforms. So we take this particular paradigm and we stick it to the Metal-Chalcogenides and to phase change. We either nanostructure a plasmonic metal, and by nanostructuring the plasmonic metal, we create these nice resonances, optical resonances, that then we put a nice Metal-Chalcogenide right next to it. So a layer of a Metal-Chalcogenide is deposited next to your plasmonic metal that's been nanostructured to have a particular resonance at a wavelength of interest to you for your applications. And by changing the refractive index of this material system based on that phase transition, which I just showed you in a couple of slides back, what we can do is we can create these tunable resonances, so we can switch the resonance from one wavelength to the other, and this creates very large optical contrast at our operation wavelength that wouldn't be available naturally in the unstructured material. We can either do this in a hybrid way by combining chalcogenide with a metal, or you can take the high refractive index of the chalcogenide itself and cut out the costly gold or silver, that's the major cost component in these devices, and nanostructure the chalcogenide itself, the phase change material itself, and this allows you to be able to get very nice resonances that then you can switch again without the need to use an optical, to use a plasmonic metal in the device as well. This allows us to be able to have dynamic control over intensity, polarization, phase, beam steering in sub-wavelength devices, and absorption and other things in the sub-wavelength devices. So just a couple of slides, just opening up the fiber side of things. So as I said, we can put these on the tip of optical fibers and create very nice tunable devices. This is a particularly interesting device. In this particular case, we have a switchable metasurface that we put on top of on the tip of an optical fiber. This is a scanning electron microscope of the fabricated device, and you can see that by changing the period of these little cubes, we can change the wavelength of operation and create very high group delay dispersions, the equivalent of a 1 meter optical fiber and a 200 nanometer little tip of a fiber that we can switch and collapse back and forth. So these are great for phase shifters, for intensity modulators, and a compact, very compact environment. You can dish the chip and put everything on the fiber itself. Similarly, we did the same, as I said, with the side polished fiber. Side polished fibers are a very interesting platform. Depending on how the distance you've polished between your core to your material system that you're depositing on the side of the fiber, you can control the transmission contrast, and by changing the thickness of your material, you can tune this across various wavelengths. So you can move this across the O, E, S, C, L band of the telecommunication network being used for your broadband internet globally. And again, these are some electron microscope images. So you can see that we can create these very reconfigurable devices that now do not rely on volatile transitions. We do not need to pump these modulators like we're doing in all our telecom networks anymore. With these platforms, you only put power in to make a transition happen. You do not need to keep powering it to be able to keep it in that particular state. We've also done things on neuromorphic computing. The major factor here is simulating 5 seconds of brain activity takes 500 seconds and needs 1.4 megawatts of power on IBM Blue Gene supercomputer. So our von Neumann-based computing systems are very inefficient. We need much better computing protocols to be able to deal with much more uncertainty and bigger data sets in the coming years from a neuromorphic and a quantum computing perspective. So we've done things like create Chalcogenides, fibre, optical axons, and photonic synapses that are very useful in this realm as well. And what we've done is we've recently taken this further, and we've reduced these down to the silicon photonics level, which much smaller modulators. So we're going for the fiber to the absolute waveguide level, where things are much smaller. And the transition that you see between going from a non-volatile to a volatile, from a volatile to a non-volatile, from a volatile to non-volatile mechanism allows you to be able to not just save on power consumption, but on footprint as well. So current modulators, Mach Zehnder modulators being used across the entire telecom network are based on weak volatile thermo-optic and carrier modulation effects. So you constantly have to power these devices in your network. That's why those racks that I showed you are so red hot with heat. We are pumping these things constantly. So, and the other thing is, because of the tiny little transition, as I said, the Chalcogenide has a 2.5N transition. These have much smaller transitions. We have to propagate the signal over a much longer distance to be able to get a particular switching effect that accumulates and gives you a stable transition. So if you're looking at typical technologies like silicon nitride thermo-optic devices, the device sizes are on the order of 0.2 to 1.6 millimeters. If you look at things like carrier modulation, ITO, or lithium niobate, which is being widely used around the world for modulators and has picked up a lot of steam recently, actually, as well. Again, devices are on the order of 0.5 to 5.2 millimeters. If you're looking at for a full pi, 2 pi phase shift, and you have to constantly pump these. If we go to our device platform, which relies on very high refractive indices and very large modulation contrast, you can reduce your device size from millimeters to micrometers, up to 100 to 1,000 times smaller physical footprint than most conventional devices. This means that we can pack more, we can have much lower power consumption and a lower footprint. So per chip, we're going to have much more qubits and much more synapses in emerging quantum and neuromorphic systems. And this allows us to increase our computing power while actually drastically reducing the power consumption that we encounter in these devices. So this is an optical microscope image of some of the sample chips that we're investigating these days, and this is a work in progress where we're doing lots and lots of work in this space alongside many other groups, from the big giants like Intel and IBM and Samsung and Huawei and everyone else, to hundreds of research groups around the world. This is one of the hottest areas of nanophotonics currently, in trying to get green computing platforms that can deal with big data applications in the coming years. So I'm going to switch over for the last couple of slides and just tell you a little bit more about the photovoltaic side of things, with a view to these metasurfaces that we can make. So we nanostructure these different materials, and we nanostructure them, obviously, as I said, for green computing, but also just to create much more efficient or building integrated photovoltaic devices. So one of the things that I just want to highlight here for you all is our work on college-tunable perovskite photovoltaics. So you may be familiar with perovskite solar cells. They are a major area of research right now in photovoltaics and solar cell technologies. Perovskites are effectively they're solution process films that you can deposit, and they're great for a number of different photovoltaic platforms. What we've done is, by nanostructuring of perovskite, in this case MAPBI3 iodide perovskite cell, what we can do is we can change the color of these layers, perovskite layers, across most of the color space in the visible. So by changing the design of the metasurface, you can create a solar cell that has any color you need. And if you're familiar with building integrated photovoltaics, there is a large movement in the photovoltaics industry to integrate solar cells on photovoltaic devices onto the windows in various buildings, into the facade of these giant skyscrapers, and have a way of generating energy on the building itself. So building integrated photovoltaics. A big part of that is trying to create much more aesthetically pleasing cells, things that are solar cells that are colorful, that have particular colors, so they can be integrated as part of buildings, and they're not eyesores to the general population. So a big part of the perovskite photovoltaics community is coming up with different compositions and different chemical alloys of the perovskite crystals or perovskite solutions that allow you to have slightly different colors. So in this particular case, what we can do is we can take, regardless of the material system, you make your solar cell the way you want to make it, and we can nanostructure it then afterwards to create the effective color that you need. So we decouple those two from each other to a certain extent. Obviously, there's variations in light matter interaction that do occur as part of this. And this allows us to be able to have a very easy and simple method of creating color tunable photovoltaic cells. We've taken this a little bit further recently, and we're using rigorous coupled wave analysis techniques, which are very, very strong techniques, computationally efficient techniques to create very, very complex nanostructures and devices. And by using things like rigorous coupled wave analysis, we can parameterize the geometry very quickly, define very application-driven figures of merit that allows us to then be able to create a large number of different effects in photovoltaic devices. We can create asymmetric transmission. We can tune the amplitude of the diffraction orders to reduce reflections or enhance reflection in certain systems, for solar concentrators and thermal solar applications, for example. And we're going to we're starting to look at also looking at 3D versions of these, where we're not just looking at a singular axis, but multi-axis sort of control of the optical properties of these devices. I'm going to tell you a little bit about the asymmetric transmission as the last thing I'm going to cover here. And asymmetric transmission, you can imagine that most of the efficiency issues that we have in photovoltaic cells, obviously there are things on the material level that we can improve, there are things on the electrode level that we can improve, there are many things that we can improve, but from a fundamental standpoint, light comes into a particular device. So let me just open this up. So light comes into a particular device, and one of the major losses in any photovoltaic system is the back reflection. As soon as the light comes in, we get a huge amount of that light reflected back. And there are many, many anti-reflective coatings and various other things that have been designed to be able to mitigate or reduce this back reflection, this reflection of the solar light going into a particular solar cell. So asymmetric transmission is a metasurface way of dealing with that. By designing these very careful meta gratings on either side of any solar cell, what we can do is we can create asymmetric transmission that's tunable across much of the spectrum, all the way into the infrared part of the spectrum. So we can create very nice bands where light comes in. As soon as it comes in, it will not have the same efficiency going out, and much of it will be captured by back reflections inside the cell. This is a major way of being able to create much higher efficiency cells without having to redesign your material system, drastically change the photovoltaic cell that you're dealing with. These metagratings could be electrodes themselves, or they could be just encapsulation layers around your cell. So this is a very, very nice paradigm. We're fabricating these right now. In fact, actually, this is a little bit of an older slide. We've already fabricated the first set of these, and we're looking at various different designs, and we're doing lots of different parameterization on these to try and understand the maximal capability of these platforms. One of the things that I'll show you here, for example, is just by adding these gratings on either side of a perovskite cell, we can increase the total absorption by up to close to 20% while not changing anything else. That is a huge change in a photovoltaic platform without having to change majorly your device platform. No grating on top or grating on top of metal side, both sides, and we can get very large changes in our total absorption from the incident light. So metasurfaces and this design paradigm allows us to be able to decouple materials from the efficiency side of photovoltaics and really create much more efficient photovoltaic devices. So with that, I'm just going to end on 2 or 3 sort of propaganda slides in case anyone is interested. We're very happy to collaborate with various groups around the world. We have large active collaborations with many different groups globally. So if you're interested in some of this research, we have lots of facilities to make these materials, nanostructure these materials, simulate and model these materials. We have the largest selection of phase change materials globally. We can make them through CVD and PVD techniques, thermal evaporation, lots of different material systems. And we also do lots of these traditional materials, the transparent conductive oxides. We can make them, nanostructure them, and design and simulate devices around them. So we have large inverse and forward design platforms as well. So some pictures of the sort of group, the geniuses working on all of these within the group. And with that, I'm just going to sort of end it here, and sort of hopefully some of these different platforms that I showed you will allow us in the future not to just to have faster computing and telecommunication and photo devices and more efficient photovoltaic devices, but also devices that are much greener, lower in power consumption, much more efficient with lower thermal footprints in the coming decades. So green sustainable computing starts from the material and goes from there all the way up or through the different platforms, from the atomic to the device and to the network integration. It is a holistic approach we need to take. I hope that this talk was inspiring to you. And with that, I'm going to end, and I'll be available for any questions and answers on the day. Thank you very much.